And we're going to actually go a little bit backwards. We're going to go into probability and what's called probability distribution. You know, figuring out the probability of a success or sometimes a failure with things that are going on, but it does basically become basic probability. So for instance, when you're trying to figure out the success of something, you take the number of successes over the successes and failures. In other words, the total number of things that can happen, or the failure over the total. Okay, these are just a fancy way of saying total occurrences. What are the total number of possible things that could happen, whether it's a good or a bad thing? So, depending on what the problem is and how you're going to tackle it, you may have some different ways that will be easier, or in some cases, just the way that you have to deal with it. So, for instance, they talk about here in example 1, when 3 coins are tossed, what's the probability that at least 2 are heads? That's not one where you're going to be able to do something directly. You can't just say, like, you know, well, it's half each time when a coin's flipped, so it's a half and a half and a half, because that's not true when it has to be at least 2 heads. So here, this person wrote out the different possible outcomes and then looked back and said, well, 4 of them have at least 2 heads, so my probability of getting at least 2 heads would be the 4 successes over the 8 different possibilities, or 1 out of 2. So sometimes drawing a picture or just writing out the outcomes is a legitimate way of doing things if it's a smaller sample space. However, let's say there gets to be a little more complexity to things. Let's say when you get to another example, what's the probability of picking 4 fiction books and 2 biographies that consists of 12 fiction books and 6 biographies? This is going back to what we were just doing. Your number of successes for the fiction books would be out of 12, I'm going to pick 4. And for the biographies, it's that I have 6 and I'm going to pick 2. And I'd multiply those 2 things together. And I'm doing that whenever I'm doing probability. So what I do is I'd multiply those 2 together, but then my denominator is the total number of possibilities. Well, there's 12 fiction books and 6 biographies, so I have 18 books to choose from. And if I pick 4 from the fiction and 2 from the biography, that'd be 6 total. So what I would end up doing in a situation like this, so you can actually see where the math is coming from, is I'd do my 12 combination 4, okay, I'd get my answer. Then I'd do my 6 combination 2 and get my answer. So I'd multiply those together. So I'm just going to come over here. So my numerator would be 7425. And then I'd do the denominator. 18, pick 6. So 18,564 possible ways to pick 6 when I have 18 books. And depending on what you're asked, sometimes you may just be asked to put it in its simplest fraction form. And that's typically what I assume if they don't ask otherwise. Oops, I hit the wrong button. Why is it doing that to me? Silly thing. It wants to keep going to this. But okay, I'll let it run this way for right now. They wanted me to go to a percentage. So if I rounded that to the nearest percentage, or the nearest tenth, I'd get about 40%. If they don't tell you specifically whether to go to a percentage or a decimal, like they did here, or a fraction, you have the choice. Okay, you can do any of them. So just something to keep in mind as I squish that right out of the way. Okay. So when we get into doing it, a lot of our work's going to end up looking like this. So for instance, all right, we have a pet show. A family has 3 dogs and 4 cats. Find the probability of each of the following if they select 2 pets at random to bring to a local pet show. Okay. My probability of getting 2 cats. All right. Successes. How many cats total do I have? 4. So I have 4, and I'm hoping to pick 2. That's my success. Now, my total, how many total pets do I have? 7, but I'm still picking 2 at random, okay? So my success would be getting 2 of the 4 cats. But there's a possibility when I'm picking out of the 7 that may not happen. So I'm going to go ahead. I'm going to do 4, pick 2. Okay, so that's 6. And then for the denominator, I have 7. I'm going to pick 2. Now again, at this point, I don't care if you just did simplifying the fraction. So you'd end up with 2 over 7. I'm fine with that. Or if you said, well, you know, let me do a percentage. So it looks like it might be about 28.6%. Okay, that's an option. I can do it either way. Okay, I'm fine with either. I'll probably even put both answer ways up. So the only thing that would change then, what would be the one thing that would change when I got to letter B? I have dogs instead, so how many do I have to pick from? 3 pick 2, but my denominator would still be the same because I still have 7 total pets to pick from and I'm picking it at random. So I'd have 3 pick 2, but my denominator would still be the same, so I really don't need to do that again. 3 over 21 would be 1 out of 7. And again, if you wanted to do it via a percentage, looks like about 14.3%. Okay? Either one of those, again, perfectly acceptable, unless you're specifically told to find it in one mean or another. Then, of course, we have to throw in the twist that makes this a little more interesting. What's my chances of getting 1 cat and 1 dog? Well, I got to think about these separately a little bit.
So is that where you're multiplying?
Yeah, I'm going to multiply. So how do I set this up to see 1 cat?
4,
Yep, 4 pick 1. And what about my dog? Yep, 3 pick 1. The denominator will still be the same, though, because total, I still have 7 total pets, and I'm still picking 2. But when I'm up here, let me move this over here, I'm still doing 4 pick 1, which is 4, and 3 pick 1, which will end up being 3. For 4/7. And if you've tried the probability of every possible combination, and this would be, if I'm going to select 2, I'm either going to get 2 cats, 2 dogs, or 1 cat and 1 dog. They should add up to 1 whole. 4/7, and 1/7 is 5/7, and 2/7 is 7/7, or all of them. So I know for sure that I've done it the same, they all add up. But the only way that works is if I've checked out the probability of every possible situation. Okay? So again, nothing going too bad. Number 2 works similarly. We'll try out a couple of these. We might not need to do all of them. We'll see. So Eduardo has 10 blues songs and 5 rock songs, no other music on his MP3 player. Find the probability of the following if he plays 6 songs at random. Okay. 6 blues songs. Yes, I have 10 blues songs. I would pick 6. And then what would my total be in the denominator that I'm working with? 15 songs, pick 6. So 10, pick 6, and 15. Pick 6. So, and again, oh, round to the nearest 10th of a percent. Okay, so we got to do a percentage this time. 5, oops, not 511. No. That's better. So if I'm going to the nearest 1/10%, what would that be on this one? 4.2. Now, this time we're not doing every possible combination, so these three wouldn't add up to 100. But let's do one more. Let's do letter B here. Okay, we're going to be multiplying, so we got two different things that are going together. So how would I set up for my blues songs on letter B? Okay, 10 pick 4. And what about the rock songs? 5 pick 2. Denominator doesn't change. So, one more look here. So 10 pick 4 and 5 pick 2. We'll multiply those two together. And we already know what 15 pick 6 is going to be. Yep, looks like we're going to round up to 42%. Percent. Oh, you can't see it. Percent. Okay. You got to make sure. I know, you got to keep an eye on me. Okay. So if it's in pieces, do it for each individual part and then put them together is what we're trying to work towards on that. Now, they may not always be this complicated even. They may simplify, because we always get to get some of those. So, as we head to the back, this is simple probability. Do not make it harder than it needs to be. Candy. One bag of candy contains 15 red candies, 10 yellow, and 6 green. Find the probability of each selection. Okay, first thing. Right, how many total candies are there?
31.
Okay, 31 total. So picking a red. Success is over total. Done. Okay, nothing to have to punch in, nothing complicated. Okay. What about B though? Good. Not picking a yellow. In other words, if it's red or green. I could figure out yellow and then subtract it, but that kind of seems counterproductive. So picking a green one, I just got to be careful of the wording to see little words like not in there. The ACT likes doing that too. Little words like not or all but or things like that. Not picking a red, which would be yellow or green. So again, read the question, keep it as simple as it wants to be.
So one thing about the ACT, all the answers are going to be like kind of like simplified, like the previous ones are going to be like all like 20.
They can be. Yeah, they can put answers with, in a situation like that, pi, decimal, mix them up back and forth.
But I thought they have to be unbiased. So they have to be like
You would think that, but they do switch it up a little bit. But you're right, most of the time when pi is involved in something, they do end up just putting the answers in pi. I agree. All right, now this is the one that gets a little bit more interesting, so stick with me. Probability distributions, okay? Basically what it does is it takes a sample space or an experiment and figures out every possibility that could happen, and then we can put it into either a chart or a graphic type form. So for instance, for their example, we've got 2 dice that get rolled. What they're doing here is shows the distribution of the absolute value of the difference of the numbers rolled. So like if I roll 2 dice and I get 6 and 1, 6 minus 1 is 5. If I roll 2 dice and I get 5 and 3, 5 minus 3 is 2, and so on. So use the graph to determine which outcome is the most likely. What's the probability? So they did it for us on this one. They probably somewhere wrote down every possible combination that could occur, And then it's not real clear on their graph, so I'm just going to do a little coloring here. So they not only drew you a chart of how often each thing is occurring, but they also have this over here explaining, you know, it happened this many times. So your greatest probability, so like if you were like betting with a friend, you're saying, okay, I'm going to roll these 2 dice. I'm going to tell you the difference is going to be a 1. You would have the greatest possibility of being successful because that's the one that happens most often. Okay. So here's what we're going to do on the bottom. Probability. 4 coins are being tossed. Complete the table below to show the probability distribution of the number of heads. Okay. We are literally going to draw this out because I want you to see how this could possibly work. Why? Because you can actually see where these distributions come from then. Now you could do it either via a tree type chart like we've got on the front, or you can literally just start writing them down. And I'm not sure which is going to work better for some of you. What's that? Do the tree one. Okay, I agree. I think that helps to be a little more organized. Because I did both last night, and I was going crazy with both of them. Okay, so we have 4 coins. So for our first coin, let's see, what could we get? Okay, so now, when I'm doing this, I could get heads, or I could get tails as I'm doing it, okay? So now, when I get to, and I should have done this down for them, I'll run out of room. Oh well. So then for my second coin, I could get heads or tails. I could get heads or tails for my second coin. I am going to run out of room. So then when I go to my third for each of these, again, I could get heads or tails, heads or tails, heads or tails. Oh boy. Heads or tails. And I'm going to change colors to try and make my mess a little less messy here. Hopefully you started down a little bit further than I did. I'd have been fine otherwise. And so finally, when we get to our fourth coin, again, I can get heads or tails, heads or tails. Oh boy, heads or tails. I'm really squishing now. Hopefully, wherever you are in doing yours, you have learned a good lesson from this. Not to try and squish something like this into a very small area. Because once I get that done, I can start jotting down my outcomes. And there's going to be quite a few of them. Actually, there's going to be 16 of them. Instead of just writing them down. I did them both ways last night, and it ended up taking me about as long both ways, because when I just wrote them out, I kept forgetting one of them. So this way, at least I know the first time I'm going to get all of them. Okay, so I've got 4 heads is a possibility. Heads, 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 tails. Yeah, it can be. It can be like you're doing with like Gene. Uh-huh. Or I could go heads, heads, tails, heads. Heads, heads, tails, tails. So I've knocked out that top 4 now. So then I move to here, and I've got heads, tails, heads, 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 tails, heads, tails, because again, I keep working to the top one and work my way down. So then I got heads, tails, tails, heads, and heads, tails, tails, tails. And I'm getting a brain cramp just saying heads and tails so much. So we've knocked the first 8 out. Now we just start working our way here. So tails, heads, heads, heads going up top. Tails, heads, heads, tails. And just keep working our way down. Tails, heads, tails, heads, tails, tails. So let's see, 4, 8, 12. Thank goodness, we only got to do this one more time. Tails, tails, heads, heads. Tails, tails, heads, tails. Tails, 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 heads. And all 4 tails. Woo! Got them all. So we have 16 of them total. So let's see here. What are we trying to figure out? The distribution of the number of heads. How many of our combinations gave us 0 heads? 1. And there's 16 total. So it'd be 1 out of 16 that I'm going to get no heads. Let's go to the other end of the chart. How many of them where am I going to get all 4 heads? 1. Now let's go through. 1 head. 3. So 3 out of 16.
No, the middle one.
Oh, did I miss one?
Yeah.
Oh, right there. No, wait.
No, like the middle one. Down, no, down, 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 down. The one in the middle when you circle. That's just not one thing because that's 2 heads.
Oh, there is more.
It's tails, heads, tails, heads. The one that you circle.
Oh. I'm sitting here going, what? That one. Oh, and this one. 1, 2, 3, 4. 4 out of 16, which would be 1/4. Good call. What about 2? So we got 1, 2, 3, 4, 5. 5 out of 16. And what about 3? 1, 2, 3, 4, 4. 4 out of 16, which is 1/4. Now let's count for a minute and make sure this adds up. 1 and 4 is 5. Plus 5 is 10. 14. 15. Let me check the 2's here again. 1, 2, 3, 4, 5, 6. 3/8. 1, 2, 3, 4, 5, 6. And it's important when you do find them to go ahead and reduce them, because it's nice that I can see here, because if I kept them in 16ths, I could add up and see, wait a minute, I missed one, what happened, and get it fixed. But by reducing it, so 0 is 1/16. One of them was 1/4. By having it reduced, I can actually get that in here right away. 2 is 3/8, so that's all the way to the top. 3 is 1/4. And it's just coincidental here, 4 is 1, that this is in the shape of a bell curve. That doesn't always happen with anything you do in these. But it's something that can occur in this case. So that's something when you get into a probability distribution, how often does something occur? This is what gamblers would do with certain things. You know, how often am I going to get...
So why is counting cards even need to play? Because you're just playing the game, you're just outsmarting. Same when they do like all the dice games and stuff, they can figure out the problem.
Yeah, doing the stuff mentally you can do. The problem, like for instance with counting cards, is you're giving yourself an advantage. If you can do something mentally, it's fine.
Yeah, but they do it mentally though.
A lot of them do little things to give themselves little hints. Whether it's moving chips around or things like that, to be able to do it. Because nobody could ever prove that you mentally are doing any of those things. It's when you're using a physical system, like somebody else will sit there and you're working with them and they're keeping track of all the face cards and you're keeping track of all the lower number cards, and you're sitting there thinking about something and they're either flashing you numbers or nods like, yeah, your odds are good that there's going to be another one of those. That's what they're trying to avoid.
Okay. So they could see them make it so like they win 50, like I think it's like 54% of the time, and then like you win 46%.
On card games, you can't.
Card games are just sort of ultimate.
Right. Slot machines are where they can weigh it more towards their advantage definitively. That's where they make their money.
So what, they just hire like really good card players for dealers or something?
No, it's random.
Oh, like if you're playing blackjack or something.
It's still random. It's all random. All right, so your job, practice A/B, the worksheet. Tomorrow we will play a little more with probability.
Can you help